Okay, let's dive into something that is a genuine breakthrough in AI. And no, we're not talking about another chatbot or some cool image generator. We're talking about teaching an AI to see inside the human body with a kind of precision that honestly was pretty much out of reach until now. This is about giving AI a completely new way of seeing. And it all kicks off with this really fundamental challenge. So what you're looking at here are two different MRI scans of a brain. Maybe it's the same person, just at different times, or maybe two different people entirely. They look kind of similar, right? But if you look really close, you'll see they're not perfectly aligned. Every little fold, every structure is just slightly off. And that leads us to the critical question. How in the world do you take these incredibly complex three-dimensional images and get them to line up perfectly, down to the last voxel? I mean, think about it. Solving this puzzle is actually changing the face of modern medicine. Yeah, this isn't just some neat little computer graphics problem. This is what we're calling the medical matching game, and it's one of those puzzles where getting the right answer can literally be a matter of life and death. Now, the technical term for this whole process is deformable image registration. And honestly, it's exactly what it sounds like. We are teaching a computer how to digitally twist and stretch and warp one of these scans until it perfectly, and I mean perfectly, matches the anatomy of the other. So why does this matter so much? Well, because doctors need it for pretty much everything. They use it to track how a tumor is growing or shrinking over months. They use it to compare a patient's own unique brain to a standard medical atlas to spot anything unusual. It's absolutely crucial for planning delicate surgeries and for aiming radiation therapy with pinpoint accuracy. The stakes really couldn't be any higher. Now, AI has been trying to crack this registration problem for a while now, and it's gotten pretty quick. But the methods we've been using have this big one-size-fits-all problem. They're powerful, for sure, but they're also kind of clumsy because they're basically relying on a single, inflexible tool. To really get what that means, we gotta quickly talk about something called convolutional kernels. The easiest way to think about these is as the tiny eyes of the AI. They're these little digital filters that the AI slides across the entire image to recognize important features. Things like the edge of a bone, the texture of soft tissue, or the shape of an organ. But here's the flaw, the big problem. Standard AI methods use the exact same kernel, the same set of eyes, for every single part of the image. It's kind of like telling a master painter, okay, I need you to create a photorealistic portrait, but you're only allowed to use this one big, clumsy brush for the whole thing. For the eyes, the hair, the fine wrinkles, everything. It just wouldn't work, right? And you can see that problem visualized perfectly right here. With the old method, that one uniform tool gets smeared across the entire image. The AI is forced to use the same blunt approach for hard bone, soft tissue, and fluid. It's just not efficient. And you know what? It leads to a lot of inaccuracies. So that's the standard method. It uses the same tool everywhere, which is a concept called spatially shared attention. And the result is, well, it's clumsy and suboptimal. But what if we could give the AI a much smarter way to see? And this, my friends, brings us to the breakthrough, a brand new method called SACB-Net, which is built on a really simple but profound idea. What if, instead of that one clumsy brush, we give our AI painter a full set of precision brushes and then teach it exactly which one to use for each part of the painting? The researchers behind this work put it perfectly. They said deformations are often linked to the morphological characteristics of tissue. Voxels from various anatomical regions need to be paid different attention. In other words, a brain doesn't warp and stretch the same way a bone does. It's just common sense, right? You need different tools for different parts of the job. So how does it actually work? It's this brilliant three-step process. First, the AI looks at the whole image and intelligently groups similar pixels together into what it calls neighborhoods. Think of it identifying all the liver tissue or all the vertebrae and the spine. Then, and this is the cool part, for each one of those unique neighborhoods, it generates a brand new custom-made tool, an adaptive kernel that's perfectly suited for that one job. And finally, it applies the right tool to the right place. So simple, but so revolutionary. And look at this. It illustrates the solution beautifully. Instead of that one boring, uniform color, you see a whole palette. Each color here represents a different, specialized tool being applied to a specific region. The AI is no longer just looking at the image, it's seeing it with awareness. It's paying different attention to different regions, just like a human expert would.
Okay, so we've got the brilliant idea down. Now, let's take a quick peek under the hood and see how this SAB-Net is actually built to get these incredible results.
So the whole network is structured kind of like a pyramid. It's smart. It doesn't try to solve the entire puzzle all at once. Instead, it starts with a blurry, low-resolution version of the scans to get the big picture alignment roughly correct. Then it moves up the pyramid, level by level, adding more detail and making finer and finer adjustments until it gets all the way to the full-resolution image. It's a classic course-defined strategy. There are really just three key parts to this whole thing. You've got the shared encoder, which is what pulls out all the visual information at those 5 different pyramid scales. Then you have the spatial awareness block, the SACB. This is the magic ingredient, the smart component that actually creates and applies all those custom tools. And finally, the pyramid flow estimator puts it all together, combining information from all the scales to create one final, super accurate alignment. That all sounds fantastic in theory, right? But here's the question that really truly matters. Does this clever, new idea actually perform better than the state-of-the-art methods that are already out there? Well, it's time to put it to the test. And the researchers, they didn't pick an easy test. Oh no. They chose one of the absolute hardest challenges in image registration, aligning abdominal CT scans. See, unlike the brain, which is nicely contained in a rigid skull, the organs in your abdomen, the liver, kidneys, spleen, they can shift around dramatically from person to person or even just from breathing. This means the AI has to handle some really large and complex deformations. And the results, well, they speak for themselves. This chart shows the accuracy on that really tough abdomen data set. It's measured by something called a DICE score. All you need to know is that higher is better. Our new method, SACB-Net, hits 58.8%. That's a clear win over other leading methods, and it absolutely blows away powerful models like Transmorph, which only managed to score 44.4%. But here's what those numbers actually look like, and this is the crucial part. On the left, that's the result from our SACB-Net. You can see the colored areas representing the kidneys are almost perfectly overlaid. The alignment is fantastic. Now, look at the right. That's the result from Transmorph. It's a total miss. It completely failed to register the kidneys correctly, leaving that huge chunk totally misaligned. This is the visual proof of that performance gap. To put a single number on it, that is a staggering 14.4% jump in accuracy over a major competitor on this incredibly challenging task. You know, in the world of medical AI, an improvement that large isn't just a small step, it's a giant leap forward. And this wasn't just a one-off fluke. The method also proved it was superior on 2 different brain MRI datasets, which deal with smaller, more subtle changes. In every single test case, it either met or set a new state-of-the-art, proving that this thing is a robust and seriously versatile solution. Which brings us right back to where we started. We've managed to teach an AI not just to look at a medical scan, but to truly see it with spatial awareness, to understand that different parts of us require different kinds of attention. So I guess the final question is this. If an AI can now see our bodies with this new level of detailed understanding, what currently hidden medical mysteries is it going to help us solve next?